Good day, everyone. This will be a brand new recording for our this week's lesson in EE 2165. So this presentation will be a merger of lessons 2 and 3. And by now, I would likely have to expect you that you have reviewed the material that I've sent you days before. So this will be essentially the same content of that. So the goals of this session would be first is to reinforce topics from lesson 1, so we would rehash some topics that I gave you from lesson 2. And the second one would be to explore the basic circuits of electrical circuits. So this one is mainly the topic for our lesson 3. So again, this presentation is a combination of lessons 2 and 3. So before we proceed, I would like to learn about the difference between charge and current. From the previous lesson that we had, we've defined what current is and we measure current in terms of ampere. But charge is something that is more of a basic quantity than just current. So charge is if current rather is basically the flow of charge, and I would like to explain that concept to you by looking at this equation. So 1 ampere is basically equal to 1 coulomb per second. So the relation between charge versus and current is that um, current is basically a charge that flows with respect to time. So hence we see ampere is equal to coulomb per second. So that's another um, unit of measure for current. And the basic unit of charge is the flow of electrons. So we cannot see electrons. The measurement for electron charge were obtained from laboratory experiments in the past, and it has been found out that for 1 coulomb of charge, there are 6.24 times 10 to the 18th power of electrons. So that's a huge amount of electrons that is inside in a charge. And basically, we are saying here that 1 ampere is equal to 6.24 times 10 to the 18 electrons that flows in every second. So that's a huge amount of electrons that flows in every second. If we are to break down how much electrons are there in 1 ampere of current. So I want you to familiarize yourselves with this equation because we cannot see electrons, but we can remember that 1 ampere is basically composed of 6.24 times 10 to the 18 power of electrons that flows within each second. So that's just about it. The second topic that we would like to review would be resistance. We have um, discussed resistance in the past, and in this slide, we would like to delve more on what resistance means in any material. So the resistance in any material with a uniform cross-section area of A depends on the area cross-section of A and its length L as shown in this formula here. So resistance is equal to resistivity times length divided by the cross-sectional area, where the rho is known as the resistivity of the material. So, looking at this formula, the resistance of a material is directly proportional to to its resistivity, and the resistance is also directly proportional to the length of the material itself. But resistance is inversely proportional with the cross-sectional area A. Now, for example, if we are gonna look at this electrical wire, as shown in this image here, the as we increase the length of this wire, the resistance of this material also increases. And if we increase the cross-sectional area, like say the thickness of the wire, the resistance decreases. But the physical measurements of the wire itself isn't the only factor that affects our resistance. There is also this raw, or also known as resistivity of material, that we need to consider, and I will discuss that 2 slides from now. But before that, I would also like to discuss what conductance is. So, conductance is the ability of a circuit element to conduct electric current, hence the term conductance. And this is measured in mhos, or just an inverse of ohms. So, I know it's a little bit gimmicky, but that's how conductance is being annotated. And conductance is also termed as Siemens, or S. So conductance is basically the reciprocal of resistance. So if resistance is the ability to resist the flow of electric current, conductance is basically the measure of the ability of a circuit element to conduct electric current. So in this formula, we can see that conductance G is simply equal to the inverse of resistance, and the smaller letter G is known as conductivity, which is basically still a reciprocal of the quantity known as resistivity. So I think conductance is an important topic that we also need to consider, because when you design an electric circuit, you need to be sensible of the measurements of conductance, because some electric circuit components need to be more conductive than others. And the next slide we will at in this next slide we will show you what different materials are used in electrical and electronic circuit boards. So in this slide, I'm showing you the resistivities of common materials. So looking at these resistivities, we can also derive the value of the conductivity by just getting the inverse of the resistivity. Okay, so there are three. There are four. In this example, there are four conductor materials, and these are silver, copper, aluminum, and gold. So the most common form of conductors are aluminum and copper. So these are the materials that you can see from almost all electrical wires, from your electrical appliances to your phone chargers to the power lines. And the less common conductors, which are silver and gold, are mostly found on semiconductor or microelectronic circuit boards, such as in your laptops, in your phones, and things like that. So we do not use silver and gold for as extensive conductors, because they are really expensive and you would rather use them as jewelries and things like that. Hence, we are using copper and aluminum as our main source of conductor. So moving on in the table, we have carbon, germanium, and silicon. These are semiconductors. They have um, they have larger resistivities compared to our conductors. So we will not discuss that in this course. And we also have four examples of an insulators here. We have paper, mica, glass, and Teflon, which has very high resistivities. Hence, they are insulators. And I would also like to discuss about power and energy. This is something that I haven't included in your material, but I'm just gonna discuss it anyway. So, the discussion about power and energy is important because it helps us determine what sort of electrical circuit elements we want to design. As much as possible, we want to design a circuit element that consumes less power, that has less power rating, that has less energy consumption, because we want to be more efficient. We want to have electricity savings, right? So to start with, power is basically the time rate of expending or absorbing energy, which is measured in watts. If you can look at your phone charger or your electrical appliances, almost every electrical appliances has a power rating. So this is important that you look at as a consumer because that's what your expectations are in terms of how much this particular appliance is consuming is consuming electricity. So electricity is also measured in power, which is also known as watts. And power is basically the product of voltage and current. So hence you see the formula power is equal to voltage times current. It is important that you consider power because not all electrical appliances consume the same amount of power. It depends on how much that electrical appliance needs in order to function well. Like for example, in a light bulb, there are many wattage options for a light bulb, but normally we would expect that a 100-watt light bulb would emit more bright would emit a brighter light compared to a 60-watt power light bulb. So these are just some of the things that you need to be considering about. The next thing that I would like to discuss is energy. So energy is the capacity to do work, and this is expressed in watt hours. So energy is something that your kilowatt hour meter is measuring. So energy is basically a power multiplied by time. So it is not enough that we would just consider power when we look at our electricity consumption, but rather we need to look at energy as well, because that's how we pay for our electricity bills, for example. So power and energy works hand in hand. Power is more used in ratings, while energy is used to measure how much electricity over time has been used by our electric circuit elements or electrical appliances. So let's move on to the basic features of electrical circuits. So basically, there are three features for our electrical circuits. These are nodes, branches, and loops. To start with is a branch. A branch represents a single element such as a voltage source or a resistors. In other words, a branch represents any two terminal element. So even if an element is not connected to a circuit itself, we can consider it as a branch, whether it stands alone or we connect it all together in a circuit. So looking at this circuit diagram, for example, we have five branches. So these are the four resistors and one voltage source. So altogether we have five branches in this particular example of a circuit diagram. The next the next part would be the node. So a node is a point of connection between two or more branches, usually indicated by a dot in a circuit or just a intersection of branches. So that's how we define node. So in this particular example again, we have three nodes. So we have one, two from above, and the third node would be altogether at the lower part of the circuit. So a node is not always represented by a dot, as you can see in this particular example, but a node is basically an interconnection of branches. So that's how you would want to remember what a node is, because there are many ways that you can draw and redraw a circuit diagram. It is important that the definition of node would still be the same, regardless of what your redrawn circuit diagram would look like. So we have three nodes in this example. And the third part would be the loop. So a loop is any closed path in a circuit. It is a closed path formed by starting at a node, passing through a set of nodes, and returning to the starting node without passing through any node more than once. So that's a little bit complicated definition, but looking at this example once again, we have five branches and three nodes. And the number of loops in this particular same example would be 3. So we have one, two, and three loops in this particular example. So once you determine the number of loops, I think it is helpful that you would set the voltage source or the voltage sources as the reference point for the loops. So in this example, once again, I'm showing you that there are three loops that you can obtain. So yeah, in order to remember how much nodes, branches, and loops there are in a single circuit, you need to consider this equation. So branches is equal to nodes plus loops minus 1. So this is like the network topography that we have in order to determine the correct number of branches, nodes, and loops in a circuit. So in this particular same example, we have known that there are five branches, there are three nodes, and there are three loops altogether. And that number of parts satisfy this equation right here. So that's how you would have some sort of sanity check in order to assert whether you have arrived at the correct number of branches, nodes, and loops. You cannot have more or less. So you need to follow this equation right here in order to have some sort of checking. So, the next topic that I'd like to discuss would be Kirchhoff's laws. So, in our previous topic, we have discussed Ohm's law, and that's basically the relation among voltage, current, and resistance. Now, Kirchhoff's laws is rather a interrelation between nodes, branches, and loops. So, Ohm's law and Kirchhoff's laws work hand in hand in order to create a seamless and powerful tool in analyzing circuits. So there are two parts in Kirchhoff's laws. The first part would be the Kirchhoff's current law or KCL. It basically states that the algebraic sum of currents entering a node is zero. So take note of the term algebraic sum. And Kirchhoff's law is current law is based on the law of conservation of charge, in which in a single node, the amount of charge that enters a single node is the same as the number of charge that leaves it. So looking at this diagram, we have four examples of current. We have two currents entering, current A and current B, and we have two currents leaving this node, current C and current D. For the node above, the algebraic sum of the four currents entering the node must be zero. So we have positive notations for currents A and B, and negative current notations for currents C and D because they are leaving the node. So if you're gonna sum it up, the algebraic sum should be equal to zero. And that's if we consider the nodes entering the currents entering the node. But if we're gonna take it the other way around, for the currents leaving the node, currents A and B would now be negative, and currents C and D would be taken as positive. But still, the algebraic sum would equate to zero. But for the purpose of simplicity, the sum of currents entering a node is equal to the sum of currents leaving the node. So that's how you would just remember what Kirchhoff's current law or KCL basically states. So the amount of current that enters a node is the same with the amount of current that leaves the same node. So the second part of the Kirchhoff's laws would be the Kirchhoff's. Now, how do we um, calculate KVL by KVL? So when we say loop, we can we can have two directions for our loop. We can have either clockwise or counterclockwise. So The same with KCL, the algebraic sum of the voltages within a loop should still be equal to zero. So if we are gonna take clockwise direction for our loop, we have V1 as represented as a negative voltage, V2, V3, and V5 will be represented as positive voltage, and V4 will be represented as negative voltage. But if we're gonna consider a counterclockwise direction for our loop, the sign conventions would just be reciprocated. Our V1 and V4 would now be taken as positive voltages, while V2, V3, and V5 are all negative voltages. So why is that so? So when we consider either clockwise or counterclockwise direction for our loop, we need to look at which sign in that voltage does our loop hit first. So in the clockwise direction, like for example for V1, it hits the negative terminal first. Hence, we treat V1 as a negative voltage, and the same is true for V4. But if we treat counterclockwise as the direction for our loop, the positive terminals of V1 and V4 would be hit first by the loop. That's why we treat them as positive, and the rest would be treated as negative. Either way, the algebraic sum of all voltages around the loop would still be equal to zero. So that's what KVL basically states. So rearranging the terms, we have V2, V3 plus V5 is equal to V1 and V4. So KVL can also be interpreted as the sum of voltage drops is equal to the sum of voltage rises. So in the principle of KVL, we need to learn that connecting several voltage sources doesn't mean that you will automatically add their voltage values. We need to be sensible of their sign conventions as well, because they do not algebraically add automatically. We need to consider that if the terminals of these voltage sources are of the same, they will cancel out each other. Like for in this particular diagram, we have um, voltages 1 and 2 would sum up, while voltage V3 would would reduce the sum of our voltages. So in we also need to remember this because KVL is a bit trickier than KCL. Oftentimes, voltage sources such as in this particular example V1 and V4 have specific predetermined sign conventions because they are voltage sources. And that is true in most problems. But for other circuit elements, such as these resistors, which are represented by V2 and V3, and this other circuit element, which is represented by V5, you need to remember that their polarities depend on the nearest connected voltage source, and which is in this particular example V1 and V4. This is indicated by these red arrows in this diagram, following the polarity of the adjacent voltage source. So we're gonna discuss that more on our sample problems. The third topic that I'd like to discuss to you in this lesson would be the difference between series and parallel circuits. So, two or more elements are in series if they exclusively share a single node and consequently carry the same current. So, in a series circuit, current is equal or the same throughout. But we also need to note that sharing a single node also means that they are on the same loop. So, in series circuit, we are considering just a single loop. But if there are two or more elements are in parallel, if they are connected on the same two nodes and consequently have the same voltage across them. So if series has the same current, parallel circuits have the same voltage consequently. So for series circuits, current is equal while voltage would be divided, while for parallel circuits, voltage would be equal but current would be divided because um, we have two or more branches that share the same set of two nodes. So just a comparison between series circuits and parallel circuits, we have this table right here. So as I said, in a series circuit, current is equal across the circuit elements, while for parallel circuits, current is divided among circuit elements. And for voltage, for series circuit, voltage is divided among circuit elements, while for parallel circuits, voltage is equal across circuit elements, provided that they share the same set of two nodes. And from the diagram itself, it is obvious that series circuits share a single node or loop, while parallel circuit, the branches or the elements are connected to the same two nodes. The fourth lesson that I'd like to discuss to you would be the series resistors and voltage division. So um, how do we measure the equivalent resistor and the voltage that is divided between among the resistors in series? So the equivalent resistance of any number of resistors connected in series is the sum of all individual resistances. So that's very straightforward. So in a series circuit, if the resistors are in series, their equivalent resistance would just be the simple sum of these resistances. However, in order to get the voltage of each resistor in series, we need to use the principle of voltage division. The derivation of these formulas would be found in the textbook. If you want to learn more about that, you can browse through the textbooks. But in order to provide you with a ready formula, this is how you would calculate the voltage for each resistors in this particular diagram. So for V1 and V2, we have the voltage for each of these resistors would be directly proportional to the value of the resistance. So the voltage source V is divided among the resistors in direct proportion to their resistances. That is for resistors in series. Borrowing from Ohm's law, where V is equal to current times resistance, voltage V again is directly proportional to the value of resistance R when current I is constant. We need to remember that current is constant or current is the same or equal throughout because this is a series circuit. Hence, the larger the resistance, the larger also is the voltage across it because they are directly proportional. So the next thing that I'd like to discuss would be parallel resistors and current division. So we have discussed earlier, just a while ago, about series resistors. Now let's move on to parallel resistors. Now the equivalent resistance for resistors in parallel is equal to the product of their resistances divided by their sum. So this is basically the inverse sum of resistors when they are in parallel. So to simplify that formula, we have equivalent resistance is equal to R1 times R2 divided by R1 plus R2. So if you add another resistor, so you will just basically add R1, R2, R3 divided by R1 plus R2 plus R3, so on and so forth. So that's how you calculate the value of the equivalent resistance for resistors in parallel. Now, why do we discuss current division? Because in a parallel circuit, voltage is equal while current would be divided. Hence, we have different values for current for each branch. So we will use the principle of current division in order to get the current through each circuit element or branch connected in parallel. So in this formula, we can see that the current is divided per branch or per circuit element in this particular example. So, looking at the formula, the current I is divided among the resistors in inverse proportion to their resistances. So, I1 here is equal to R2 divided by R1 plus R2 times the value of the current I. While for I2, we have I2 is equal to R1 divided by R1 plus R2 times the value of I. So you can observe that uh, the value of I1 depends on the resistance R2, while the value of I2 rather depends on the value of the first resistance or R1. So the current I is divided among the resistors in inverse proportion to the resistances as I said. Borrowing from Ohm's law again, where I is equal to voltage divided by current, current I is inversely proportional to the value of resistance R when voltage V is constant, and voltage is constant in a parallel circuit. Hence, the larger current flows through the smaller resistance or the path of least resistance, as what you've probably heard somewhere. So, you need to remember this because these are simplified approaches to calculating the voltage division and current divisions for series and parallel circuits. So, sample problems will be done on a separate document. I cannot include them on this presentation for now, but I will send you uh, a succinct solution for our sample problems later on. So this will be the end of the presentation. Thank you, and don't forget to leave your queries. If you have questions or comments in our communication channels, you can leave it on our chat box. You can send me an email or you can leave a comment on our Google Classroom. Thank you.